In this lesson, we're going to be looking at counting principles. We're going to be looking at sample spaces and tree diagrams. These are two ways to collect information and to figure out how many possible outcomes there are. One's more visual than the other. In this lesson, we're going to look at counting principles. We're going to look at sample spaces and tree diagrams. Both are methods of finding all the possible outcomes. For sample spaces, if we look at how many boy-girl arrangements are possible, in this topic we're going to look at counting principles. So here's an example. It says how many boy-girl arrangements are possible in a 3-child family. Now to answer a question like this and others like them, we need to know the total number of possible outcomes. We can find the sample space, which is the list of all possible outcomes, using a tree diagram or using a chart. Let's look at the tree diagram first. So a tree diagram can branch from the top down, but more often we go sideways. Now, if there's 8 possible outcomes, they're giving us this answer already, but how do we get all of those outcomes? Now you can sit here and think, okay, 3 boys or 3 girls, or first a boy, then a girl, and we can go and figure them all out and figure out what those 8 are. But as our problems get bigger or more complicated or have more variables, organizing our work in a tree diagram will be much easier. So how does this work? Let's start with the first child. So the first child can either be a boy or a girl. Okay, so starting there. Now, the second child could also be a boy or a girl. If the first child's a boy, does it determine whether the second child is a boy or a girl? No. So, first child's a boy, second child could be a boy or a girl. Now, if the first child was a girl, the second child could be a boy or a girl. So when you're reading this, right, this has to do with the first child, and this has to do with the second child. But there's not 4 children, there's just 4 possibilities. It could be boy, 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 girl, girl, boy, or girl, girl. That's the order of the children being born. But there's not 2 children, there's 3. So for the third child, you're looking at the same outcomes. So the first child's a boy, the second child's a boy, the third child could be a boy or could be a girl. If the first child's a boy, the second child's a girl, the third could be a boy or a girl, and so on. So the fact that the third child could be a boy or a girl isn't dependent on what happened previously, right? Now, it's not enough just to draw the tree diagram. Now let's list all the possible outcomes. So when we read these tree diagrams, we read across. If I'm looking at the first possibility, boy, boy, boy. So that would be listed. That means all 3 children are a boy. If we look at the next one, boy, boy, girl. So I'm just reading across the tree diagram. If your first child's a boy, the second child could be a girl, and the third child could be a boy. Boy, girl, boy. Or the third child could be a girl. And so on. So keep going through that tree diagram and write down all the possible outcomes. So now you can see there's 8 different outcomes for having 3 children. These are all the combinations of boy and girl that there can be. So 8 ways. Let's try another example. It says Hannah plays soccer. The soccer uniform has 3 different sweaters, red, white, and black. 3 different shorts, red, white, and black. How many different variations of the soccer uniform can the coach choose for each game? So again, we're going to do a tree diagram first, and then you can see below there's another way of figuring out the outcomes, and that's using a chart. And usually that's nice for more simple problems, and this one's a good one that we can try out. You can see you'll get the same number of outcomes and the same outcomes either way we do that. So the tree diagram, we're starting, instead of with 3 variables, we have, instead of 2, we have 3. So let's start with the sweaters. And there's 3 possibilities: red, white, and black. And you're going to pair these up with the shorts. Now, if the coach chooses a red sweater, the coach can choose red shorts, white shorts, or black shorts. If they choose a white sweater, we have the same possibilities for shorts. And if we choose a black sweater, we have the same 3 outcomes: red, white, or black. Sorry. So what are the outcomes? Red, 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 white, red, blue, white, red, white, 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 blue, blue, red, blue, white. I keep saying blue, sorry, it's black. The bees are all black, not blue. So how many outcomes? We've got 9 different outcomes. So let's try the same question using the chart. Now with the chart, you're just pairing them up. So here I can see red, red, so I would write that. And the next one I'd have red, black, and then the last one I would have red, white. And then you would go ahead and do this again with the next. So white, red, white, black, white, white, and then finally the last one, black, red, black, 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 white. And you can see these are the same 9 outcomes that we got above. Okay? Does it matter which one you choose? No, but in a question it might say use a tree diagram or use a chart. In other questions, like on the exam, it might say use a method of organizing. It might not even say tree diagram or chart. Okay, it'll just say something else referring to that. And how you choose to organize your work to figure it out is up to you. So just these are 2 tools that you have to use in order to figure out how many outcomes. And this is going to be very useful for this unit, but not only this unit or next unit, that's probability as well. You always need to know the total number of outcomes to figure out the probability of the desired effect of what you're trying to figure out. Now if we look at the next page, there's actually a 3rd tool which will be the most useful to you, and that's the fundamental counting principle. Because you can imagine if we've got many, many, many more outcomes, drawing out 100 plus outcomes is not something you're going to want to be doing. Not a good use of your time. So if you have one event that can be done in L ways, and event 2 can be done in M ways, event 3 can be done in N ways, then the events to be done can be done in L times N times N ways. So from our other example, the number of uniforms was our sweaters times the number of shorts. So we had 3 different sweaters, 3 different shorts, we would get 9. In our first example, for the different outcomes of boy and girl, we had 3 children. Oops, 3 children. And the first could be a boy or a girl, so there was 2 outcomes there. The second could be a boy or a girl, so there was 2 there. And the third could be a boy or a girl, 2 there. And you multiply those together, and you would get the 8 different outcomes. So those are the first 2 examples that we did, and we could have done them using a fundamental counting principle, and that would have been a lot quicker. Let's take a look at a couple more examples, and then I'm going to give some for you to try on your own before you come to class. A luggage lock opens with the correct 3-digit code. Each wheel rotates through the digits 0 to 9. How many 3-digit codes are possible? So if it's a 3-digit code, 1, 2, 3. How many outcomes do I have for each number? Well, I can put in any value from 0 to 9 here. So how many values do I have as possibilities? There's 10 different values. I could use the numbers 0 to 9 for the second one, and 0 to 9 for the third one. So when I multiply the 10 outcomes by the other 10 by the other 10, I end up with 1,000 different possible codes to be used on this luggage lock. Okay, So where can this be applied? You can think of things like passwords for a computer, where you can not only use numbers but letters and then capital letters, right? So capital letters is a different 26 values than the 26 letters in the alphabet. And then if you can use symbols on top of that, and the longer your codes get, right, more digits, more spaces that you have, you can imagine that's that many different codes, different combinations, the more secure your password's going to be. Okay. Now let's take a look at B. They're giving us some different constraints for the code. It says suppose each digit can only be used once. How many different codes are possible when repetition is not allowed? So it's really key to read the questions carefully, because they're going to give you different rules for how we figure out these problems. So it's still a 0 to 9 for the 10 different digits we can use, right? For the first one, I can still use any number 0 to 9, so there's still 10 possibilities. But what happens when I've used one of those numbers? I've used either 0 or 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9. Does it matter which one I choose? No. What matters to us is that there's only going to be 9 possible outcomes left, right? So it's not 0 to 9 anymore. One of those digits from 0 to 9 has been used, so I only have 9 possible digits to choose from. The last one here, I've used now 2 possible digits, so I only have 8 left. To figure out the outcome, I multiply 10 times 9 times 8, and I end up with 720 possible codes. So when repetition is not allowed, that means we cannot have the same number more than once. That's pretty much all there is to the fundamental counting principle. Now I'm going to ask you to go through the next couple of examples. Let's take a look at them together, but you're going to try them out, okay? And then we'll go over them in class. So example 3 says, given the digits 1, 2, 3, 4, 5, 6, 7, 8, 9, how many 4-digit numbers can be written if the digits can be repeated? How many 4-digit numbers can be written if the digits cannot be repeated? Very similar to the ones we just did. And then C says how many even 4-digit numbers can be written if the digits cannot be repeated. So try those ones out on your own. We'll go through them. Example 4. A computer store sells 6 different computers, 4 different monitors, 5 different printers, and 3 different multimedia packages. How many different computer packages are available? Try that one out. And then for example 5, in Manitoba, how many potential license plates exist using all 6 characters? Now for this one, just be aware, I know there's lots of specialty license plates. In this case, we're talking about the regular 6-digit license plate, where the first three values are actually letters and the last 3 values are numbers, and the letters that are used are all capital letters. Repeats are also allowed for Manitoba license plates, so use those rules when doing example 5. For example 6, this one's just tricky because it says how many ways can the digits 1, 2, 3, 5, 6 be arranged? Realize there's no 4 there. There's no digit 4. So when you're counting how many possibilities there are for each value, for each digit, realize that the 4 is missing. For repetitions, and then again with no repetitions. For example 7, we're looking at what happens if we're dealing with a fundamental counting principle with a race. So how many ways can first, second, and third place be arranged in a race of 8 runners? We get lots of questions that are a variation of this type of question. So that's another good one for the fundamental counting principle. For example 8, here's another digit question. How many 5-digit even numbers, again this is even numbers, can be arranged using 1, 2, 3, 4, and 5? Example 9. How many 4-digit even numbers can be made from the digits 0, 2, 5, 7, 8, and 9? And the tricky part in this question is that it's even, but also this 0. How do we handle the 0? Why, you may ask, is that extra tricky? I can count 1, 2, 3, 4, 5, 6 problems, or 6 numbers, So there's 6 numbers. That's fine. How is that different? Well, you can't have digits starting with 0. If you want that 4-digit number, that is not a 4-digit number because 0 at the beginning doesn't count. That's a 3-digit number. The only place the 0 can be, would be in the 2nd, 3rd, or 4th position. It can't go at the beginning. So that's extra constraints, okay? So see how you're going to figure that out. I want you to give all these a try. Will you get all of them? Maybe. And if you don't, that's okay. We'll go through them together in class. Let's take a look at this last example, example 10. It has to do with a standard deck of cards. And just a reminder from our last unit that disjoint means 2 or more sets have no elements in common. Mutually exclusive means that 2 or more events cannot occur at the same time. Okay, so again, here's our 52 cards, and it says count the number of possibilities of drawing a single card and getting either a black face card or an ace. So aces in counting counted as face cards. These here are your face cards: Jack, Queen, King. I drew my circle too big. Jack, Queen, King. Those are your face cards. So either a black face card or an ace. And these ones are aces. Okay, so how many black face cards do we have? There's just these 6. How many aces do we have? 4. Remember, the fact that this says or means we add. Okay, so the number of A or B, remember our rules, is the number in A plus the number in B. Instead of or, I could have said union, right? That means mutually exclusive or disjoint. Why in this case? Because if you look at the Venn diagram, these are our black face cards. Let's put that in A. And in B, we'll put our aces. So we can have the Jack of clubs, the Queen of clubs, or the King of clubs, the Jack of spades, the Queen of spades, or the King of spades. Okay? That's all of our face cards. And then the aces, we can have the Ace of clubs, the Ace of spades, the Ace of hearts, or the Ace of diamonds. And if we look at that, you can see there are our 6 and our 4. They are disjoint. So we've got 10 plus 4, not 10, 6 plus 4, I did the addition already, to give us 10. So that's the number in A union B. Black face cards or an ace. For B, it says either a red card or a 10, right? So here's A and here's B. Here's our red cards or a 10. If we look up here at our cards, our red cards are all the ones in this section here. And our 10s specifically are these 4 here. And just doing that, you can see, if I count those, these 2 red cards get double counted, right? They get counted as red cards, and they also get counted as 10s. And that's what goes in my overlap here, the 10 of hearts and the 10 of diamonds, right? So 10 of hearts and 10 of diamonds. The other 10s that we have is the 10 of spades and the 10 of clubs. And then for the red cards, we're going to list all the rest of them. So we've got ace to 9 hearts, ace to 9 diamonds, and then Jack, Queen, King of hearts, Jack, Queen, King of diamonds. So those are all the red cards. So what do we have here? We've got the 24 red cards plus the 2 red 10s plus the 2 black 10s to give me a total of 28. The other way you would have looked at this is to take all of your red cards, so your 26 red cards, plus your 4 red 10s, and then subtract the 2 that we double counted to give you the 28. Either way, symbolically, the number of A union B, when these are not disjoint, would be the number in A plus the number in B minus the number in both A intersection B. So these are not mutually exclusive. And not disjoint. You must subtract the common outcome.